The homework questions that were asked from the mid-chapter review. So the first one here is question 3, and we have two vectors with an angle of 120 degrees between them. The magnitude of A is 3 and the magnitude of B is 4. So maybe something like that. And we know that that's 120. So part A says that we should calculate the magnitude of A plus B. So this is going to be with our head to tail diagram, redrawing B at the end of A, and then I'm going to draw in my resultant vector. I know that with the C pattern, that angle that corresponds with or the co-interior angle of the 120, that would be 60 degrees. So if I redraw this diagram, we have the magnitude of the resultant, which is A plus B, and 3, 4, and 60 degrees. So here we have that the magnitude of the resultant squared, 3 squared plus 4 squared minus, whoops, I'm making up a new cosine law there, 2 times 3 times 4 times cos 60. So the magnitude of the resultant doing this on my calculator, is root 13, which is about 3.6 units. Now, if we wanted to find the angle in here, and I wonder if, I'm not sure if this is going to be a case that's the ambiguous case with the sine law, because this is actually one that may go that way because it's across from the biggest side. So I'm actually going to use cosine law to solve for theta, because this could be an ambiguous case. So So I'm going to use the cosine law to solve for theta. So cos -1, and if you memorize this, I don't, but I probably should. 3 squared plus 3.6 squared minus 4 squared over 2 times 3 times 3.6. And then we can figure out, I'm wondering if that might be what got some people on this question, if maybe that is actually an ambiguous case. 5.96 divided by 2 times 3 times 3.6. And no, it's not. So that is 73.98 degrees. So about 74 degrees for the angle between A and A plus B. So that angle in there is that about 74 degrees. The next one, determine all possible values for t if the vector x, which is t times vector y, is 4 times the magnitude of y. So basically, we have some scalar multiple of vector y. And I'm just going to kind of show this visually. And we have a scalar multiple of y that gives me vector x that's 4 times its magnitude. So we could have something like that gives vector x as 4 times vector y. And the other possibility would be if it went in the opposite direction. So if you'd multiply that by -4, we know that the magnitude has to be 4 times the original magnitude. but magnitudes are always positive. It doesn't tell us about direction. And since all scalar multiple vectors would have to be collinear or have to be parallel, there's only two vectors that are parallel to y that have a magnitude 4 times that vector. It either goes the same way as y or in the opposite direction. So t could be 4 or t could be -4. And those would be the only possibilities that would work for that. Next one, number 6c. So this says, given the magnitude of u is 8 and the magnitude of v is 10 and the angle between them is 60 degrees. This is asking us for c, and that's the unit vector in the direction of u plus v. So there's u, there's v, and it's a 60-degree angle between them. One magnitude's 8 and one is 10. So I'm going to figure out where u plus v goes, or more in particular what its magnitude is. So that's that resultant vector. Again, I need to use that C pattern just like in the first example here, and that would give me 120 degrees up there. So the resultant, which is u plus v, or r squared, is going to be 8 squared plus 10 squared minus 2 times 8 times 10 times cos of 120. So the magnitude of u plus v calculator out, is about 15.62. And I believe that this one had a note in the outline that the answer in the book was wrong. And I think actually in the textbook it left this magnitude as an exact value, which is the square root of 244, and reduce this to a mixed radical. So I know that 4 goes into 244, and it's 4 times 61, so that would be 2 root 61. So the unit vector, which would be a vector that's in the same direction as the resultant but only 1 unit long, is going to be 1 over 2 root 61 times vector u plus v. So times that resultant by the 1 over the magnitude of it. And I do think that one was wrong in the textbook, but make sure you're checking on the outline because there's corrections written there. Okay, so vector m is collinear to n, but in the opposite direction. Express the magnitude of m plus n in terms of the magnitudes of m and n. Okay, that's a lot of words. Let's try and draw a picture. So we've got vector m and vector n. These are collinear vectors, but going in the opposite direction. If we had vector m plus n, so if I went along vector m here, and then head to tail, vector n is going to take me backwards, then the start to end, we aren't really making a triangle here because we're going right kind of back and forth along the same line. This green one would be m plus n. So the resultant vector, when you add two vectors that are in opposite directions, really we're going to have the difference in their magnitudes. So the magnitude of m plus n, and normally this is not true, only if it's collinear can we do this kind of calculation. Here would be the magnitude of m, how long it goes in one direction, minus the magnitude of n. We don't know, however, that m is longer, right? The magnitude of m might be smaller. That might be the smaller vector. So what if that was the case? Then we would have m going this way, but it's littler, and then n going this way, and then m plus n would be, so let's say in this example, what if that magnitude was 5 and that magnitude was 8? I couldn't say that the magnitude of the resultant was 5 minus 8 because that's a negative and magnitudes are always positive. But it would be kind of the opposite of that. It would be 8 minus 5. So here, that would correspond to that diagram. And here, the magnitude of m plus n is equal to the magnitude of n minus the magnitude of m. So it's the bigger one minus the smaller one. And one way of writing this in general, we want to subtract this and only take the positive value. So the magnitude of m plus n is going to be the magnitude of m minus, I'm going to need a bit more space in here. So the magnitude of m minus the magnitude of n, but we're going to want to take the absolute value. So just the positive difference between those two lengths. So that's always positive. Okay. Last one from the homework questions. We have a quadrilateral PQRS. So let's draw, and it doesn't specify what this is. So I'm going to very specifically not make it a square or a rectangle or a trapezoid or anything in particular. Okay, so we have PQ is 2A and QR is 3B and QS is 3B minus 3A. Okay, so we want to express PS and RS, and I think the question here is just asking for RS in terms of A and B. So if I want RS, I'm going to want to find a path that goes from R to S along things that I know about. So I don't know going straight from R to S, but I do know something here and I do know something here. So I'm going to choose that path. So I'm going to say that RS equals RQ plus QS. And I don't actually know RQ, but I do know QR. So RQ is the negative of QR. And I'm going to leave the QS as it is. And then I can substitute in the 3B into negative Q, into the QR, and the 3B minus 3A into the other one. So here I'd have negative 3B plus 3B minus 3A, which gives me negative 3B plus 3B minus 3A. So then that will simplify to be just negative 3A. Always look at paths to get what you want in terms of the things that you already know. And just to kind of go over the ones that I did take up in class in case anybody missed it from the day 7 homework. This one I think is pretty self-explanatory. Just noticing that your components for x have to be equal, the components for y have to be equal, so I kind of came up with an equation there, and then the components for z also have to be equal with another equation there, and then using that to solve for a and c. For part B, if 2 points are the same, then of course they would be the same distance from the origin if they were the exact same point. Okay, this one is also was in the lesson for lesson day 8. This is kind of a specific case of how we could find the distance from a point to the origin using Pythagorean theorem twice. So this point here, say point P, we kind of envisioned the cube or the rectangular prism, the box, and then broke this up into 2 different triangles. So the first triangle here is along the flat bottom of the box. We know that the 2 sides of that right angle triangle are 10 and 5, and we can figure out that the distance across the bottom, that diagonal distance across the bottom, is the square root of 125, or x squared, that distance across the bottom, is 125. Then we kind of looked at this triangle up here. You can see it highlighted in green there. And that's the distance we really want, that hypotenuse. But the distance across the bottom, which is that diagonal distance through the rectangular prism on the bottom side of that, as well as the vertical height of the rectangular prism, are 2 sides of a right angle triangle. So here we said that x squared plus 10 squared equaled d squared. And then we knew from the other triangle what the x squared was and sub that in there. So that's how we proved that that distance was 15. And in the lesson 8, that's done in kind of a more generalized way using like x1, y1, z1, and x2, y2, z2. And that is it. Other homework questions I will take up in class tomorrow.